Okay, number 9, it's radical questions, and it's asking you to take the cube root of negative 64, which we can do. Now listen, if these are all terms together, you can individually take the cube root of each piece. Whereas whenever you have a plus sign, with everything we do in algebra, you have to be a little more careful. But anyway, you can do these separately. So the cube root of negative 64 is perfect. It comes out of that radical as negative 4. The other two, not so perfect. And it's been a little while since we talked about this. But the rule for the exponents is it has to divide by the index. So 8 does not divide evenly by 3. So we want to try to break it up some way, like a to the 6th times a to the 2nd. So we have the largest thing under 8 that divides by 3. A6 divides by A3, brings that out as an A squared. Leaves an A squared left over in. B5, I'll call that B3 times B2. And then B to the 3rd with the cube root comes out of that radical as a B. So what you have left in is an A squared B squared. Now another way of thinking about that would be, if you were doing the cube root of A to the 8th, you could say it's A. It's A times itself 8 times, right? So any 3 sets, kind of our factor tree thought, any 3 of a kind comes out as one of those. So you're able to bring out one A, that brings out another A, so you brought out A squared, and then the leftover, there wasn't enough of it, is A squared left in. Does that make sense? Same thing with the B to the 5th. You could have written it out longhand, so that means 5 B's. Because you're doing a cube root, it takes 3 of those to bring out 1. So we're able to bring out 1 B, and it left B squared in. And then the negative 4 just came out of that because the cube root of negative 64 was perfect from the get-go. Negative 4 times negative 4 times negative 4 is negative 64. Okay, another way I want you to think of this is it could be written like this instead of a cube root. It could say to the 1/3 power. And I just wanted to remind you that a cube root and a 1/3 power means the same thing. Okay, we do the same deal with it. Okay, number 10. So number 10, still on the radical theme. You want to reduce these before proceeding. So these are not like radicals, but there may be a way to reduce them so that they are, and that's exactly what happens here. When you reduce this first radical, since you're doing a 5th root, it's like I said before, you want to bring out the combos of 5. So you can bring out of that 2 sets of 5s. Or think about that as being M5 times M5 times an extra M1. Or if you show that all the way out, you can really see there are 11 M's. You bring out 2 sets, come out of there as M squared. You've got a 9 already there. You brought out an M, or an M squared with an M left in. Because you're doing a 5th root. P7 would be like P5 times P2. There's a set of 5 P's which brings out 1, or 5 divided by 5 brings out P to the 1st. So what's left in is the 5th root of an M P squared. Now this other one, 5th root, those are smaller than the roots, so it's not going to reduce. But it is, just so happens to be, a like radical. These two are a match. So if you have matching radicals, you can add or subtract those. So we have 9p squared, 9m squared p minus 7m squared p. Those are alike. So we can subtract and say we have 2m squared p of that radical. It's just combining like terms. These were like terms, exactly like terms, and we were able to combine those. Okay, number 11. What I would recommend on number 11 is multiplying the numerator together first, which you're allowed to do because you're multiplying and they're both cube roots, so So we're allowed to multiply those parts together. And then divide it by the denominator. Okay, so when we multiply the numerator, we've got a 27 times 3, which is 81, and an x times y to the 4th. y2 times y2 is y4, and these are both cube roots. And it just so happens that you're allowed to reduce, by the way, if you're dividing like bases or like indexes, you can reduce this stuff in there. You can consider that to be one big cube root dividing. So the x's and the y4s just drop out for you. And even 81 over 243 reduces to a 1/3. In other words, everything cancels except the 3 on the bottom. So this becomes 1 left on the top, since it all canceled, over the cube root of 3. Then we're not allowed to leave it with a radical in the denominator. You're not allowed to have radicals or imaginaries in the denominator of the standard form. So we have to then times it by something to make that perfect. So you've got a 3, so it takes 2 more 3s to make a set of 3, right? You're doing a cube root, so you need 3 3s before you can bring out a 3 to make it perfect. Or if you just want to think of that as 9. You need a 3 times 9 to get 27, so then that's a perfect cube, and then it can be out of the radical as 3. Whatever you do to the bottom, you have to do to the top. I'm going to just go ahead and say that's 9. So 1 times cube root of 9 is cube root of 9. And then what I want you to see here is a cube root of 3 times 2 more cube roots of 3 makes the cube root of 27, which then is perfect, and it's not in the radical anymore, just regular 3. Or if you think I have 3 3s, since I'm doing cube root, that brings out a 3. Okay, and then this is your final form of the answer. Okay, let's try to do one more of this type. Number 12. This would actually be the end of the chapter R stuff. When you get to number 13, 13 starts chapter 1. Okay, so number 12, you have radicals in the denominator. So I want to rationalize that. Just like I said on number 11, you cannot leave a radical in the denominator. But on number 11, it was just that one term, just the one term where you times by whatever it needs to make it perfect. When it's a two-termer, a binomial, you have to times by the conjugate to fix that situation. So the conjugate would be 7 radical 2 plus radical 7. Conjugate, remember, just means change the sign of the binomial. When you FOIL that, you're guaranteed to have a rational number. Whatever you do to one part, you have to do to the other part. So we do the bottoms first. I'm going to FOIL this. The first times first makes a 49, 7 times 7. And radical 2 times radical 2 will just be a 2. The square root, and you have a match, so it comes out of the 2. Or 108. No, 98, sorry. 49 times 2, 98. The outer will be a 7 radical 14, but the inner should be the opposite, minus 7 radical 14. That's what should always happen with a conjugate. The middles cancel out, the inner and outer. Then the last should be negative because the signs are different. Radical 7 is just 7. So you should have that guarantee of no radicals left after times by conjugate. So we'll call that 91 in a minute. Distributing the numerator, square root of 7 times 7 square root of 2 is 7 square root of 14. You know, just times together what's under the radicals for 14. Square root of 7 times square root of 7 is just regular 07. Square root of 49 or 7. So what we've got in the numerator, 7 radical 14 plus 7 over 91. And then we should always reduce if possible. I think 7 goes into 91. You can double check. 7 times 13. And so I should be able to reduce. If all 3 terms have a common factor, you can reduce by that. 7 into 7, 7 into that 7, and 7 into 91 is 13 for a final answer of 1 radical 14 or just radical 14 Don't forget to say plus 1. If it's the only thing holding the spot, you have to still show that. Plus 1 over 13.
You don't also show the 1 in front of the radical.
Not this one. Yeah, but a lot of times we want to drop this one even, and you can't drop it because it's holding that whole place there. It's about to see what you're doing with that.